So imagine we have this building here, and we have a bucket of water. We want to move that bucket of water to the top of the building. And let's suppose the building is 60 feet tall, and let's suppose that bucket of water is 35 pounds. So in order to find the work required to move this bucket of water up to the top of the building, like so, we can find that pretty easily as work equals force times distance. So we know that our distance that we're moving it was 60 feet, and we know that our force of the water bucket was 35 pounds. So we go ahead and multiply these together, and we get 2,100 foot-pounds. So that's a pretty simple problem, right? Final answer, done. Unfortunately, the problem is going to be a little more complicated than that, because we can't just magically move this bottle up to the top. We got to use some means to do it. So let's go ahead and move this up here, and we're just going to call it the work for the moving the bucket itself up, which is really what we want to do. But in order to do that, we may want to use something like a chain, as shown here, to pull that bucket up to the top. Now imagine if we were just going to pull that whole chain and the bucket up 60 feet like this. Well, that wouldn't be too hard. We just take that whole weight of the chain and multiply it by that distance of 60 feet and add that to the work for the bucket. However, that's not really what happens when you pull the bucket up, right? So it's really going to happen if you're on top of this building and you're trying to pull this bucket up with this chain. Well, you're not going to pull the chain all the way up, because as you pull it up, you're just going to pile that onto the side. So at any given point, you're not necessarily pulling all the chain. The higher that you get the bucket up, the less chain you're actually pulling, which makes this a little bit more complicated of a problem. And so if we want to find the total work required to pull this up, we would say that total work is going to be the work required to just pull the bucket itself up plus the work required to pull the chain up. And the work required to pull the chain up can be a little complicated because it's not a constant force. So how can we figure this out? So as a first sort of approximation here, let's go ahead and try and find the work required to move that chain up and split it into 3 parts. We'll call it work 1 plus work 2 plus work 3. So work 1 is going to be what's required to move that chain up to this height. Work 2 would be the work that will be required to move it up from that point, maybe up to this point. And then work 3 would be what was required to move this last bit. So we're just going to kind of separate this into 3 different bits here, and just kind of approximate each of those steps, and that's going to give us a little bit more accurate of an answer here. So for work 1, we're going to look at this first step here, moving up this first little increment, a third of the way up. And we can use the same formula for work as just force times distance, but we're going to call this the force F1, and our distance is going to be delta H, where our delta H is going to be defined as that first increment that we're moving it up. We'll call it delta H, and say it's 20 feet because it's just a third of the way up. So we've already defined delta H, so let's go ahead and move that over here into our equation. But now we got to find this force, F1. Now the force of this chain, we can kind of separate this out and say it's equal to the density of the chain times the length of the chain. So the density of the chain is given. That's going to be, in this case, 0.5 pounds per foot. So we can go ahead and move that down here. And for the length of the chain, L1, let's just go ahead and say that's going to be 60 feet. So that's going to be a little bit of an overestimate because we're looking at this this delta H here, and so we're estimating that chain length when that water bucket's at the bottom, not when it's up here. So we're going to get a bit of an overestimate for the weight of the chain and the total work it's going to require. But it's going to be at least the first step at this. So we're going to go ahead and move that 60 feet over here. So our force of our chain for this first increment is going to be 30 pounds. Where you can see here that the units of feet here are going to cancel out. We'll just be left with pounds. So we can go ahead and move that 30 pounds up to here. And so our work for this first section is going to be 30 times 20, which is 600. So let's go ahead and move that in to our work for the chain. Our first increment, 600. We got that. Now we can go look at the second increment. So for the second increment, we're looking at moving it up that same distance, that delta H. And so our work 2 is going to be a similar equation, F2 times delta H, where that delta H is just that 20 feet, same 20 feet, because we're separating into similar increments. And now we can just go ahead and move that 20 over. Now F2 is going to be a little bit different though. We still have the same density as before, but our length of the chain is getting smaller now. So L2, we're just going to approximate that as 40 feet. So again, it's going to be a bit of an overestimate. So again, the feet cancel out, and we're left with F2 is 20 pounds. So now we can move that 20 up here, and the work for that second increment is going to be 20 times 20, which is 400 foot-pounds. So we can go ahead and move that up here, and that's our second piece. We just got one more piece to go here. And of course, that next piece is going to be this last distance here. And we do the same idea. Work is our force times our distance here. That distance remains the same at 20 feet, so we can move that over. And our F3 this time is going to be smaller still, because while the density of the chain remains, that length is going to be smaller for this increment. And that length is going to be, let's call that 20 feet. Again, an overestimate. So you multiply these together and you get 10 pounds this time, and move that on up. 10 times 20 is going to give us 200 foot-pounds for the work in our final stage. And now we're getting close. So if we add these all together, we can find that the total work to move that chain up is going to be 1,200 foot-pounds. So now we can get an approximation for the total work required. Recall it was the work of our bucket, so we can move that over here, plus the work of the chain, which was 1,200, of course, because we're moving it up from down here. So adding those together, we get 3,300 foot-pounds. We'll go ahead and box that in. So this is our approximate answer here. It's a good first step, but as you can imagine, we could probably do a little bit better than this, right? Because we just separated into 3 increments, and as you notice, we overestimated the length of the chain each time, and we could probably do a better job than this, right? And so let's clear off some of these items here and take another look at what we just did. So to find the work for the chain, recall we added up these 3 increments, right? And another way you could state that would be we just took the summation of W sub I, where I goes from 1 to 3. So we added up these 3 different values for the work. But that wasn't quite as accurate as we can get. So let's go ahead and cross that out. And so we can cross out these numbers that we got from it too. And let's try this again. But instead of going from I equals 1 to 3, why don't we go from I equals 1 to infinity? Let's find the limit of this summation and adding up more and more of these smaller and smaller increments. And if we were to do that, we could separate W sub I just like before. Work is just force times distance. So we have the force, which is the density of the chain times the length of the chain times delta H. So the same equation we had before, but now our delta H is going to become a lot less smaller. So imagine this is going to be infinitesimally small. So imagine we're just going to move this bucket up in little increments, and we're going to keep adding the work required for each of these little increments. And those little increments, those are going to be our delta H value that's over here. Now our density of the chain, we've already found that this is it's given up here. So we got the same density of the chain, but now we're left with this length L sub I. So what are we going to do for L sub I? So we can just call that it's 60 minus however high this bucket is at any given time. So say the bucket was up here. In that case, our H is going to be how high that bucket is off the ground, H sub I. And the length of the chain is going to be 60 minus whatever that length is down here. So now we've got an equation for L as well, and that gives us all that we need down here. Now space is getting a little tight here, but let's get rid of that, and let's kind of move this up and keep working on it. So now that we've defined our length, we can go ahead and rewrite this summation, and let's go ahead and add that length in over here. So this is our updated summation. And now when you have an infinite summation, recall what is this actually equal to? Well, based on the definition of the integral, this infinite summation is actually just an integral. So let's convert that to an integral. And notice what we did here. So this delta h right here, it just became our dh, infinitesimally small. Change it in height. Now our 60 minus h sub I, well, that just became 60 minus h. So instead of these increments of h, we're just going to let h increase continuously, which is basically saying that we're just continuously pulling this bucket up as our h is increasing. So instead of h sub I here and over here, when we move on to our integral, we're just going to call those h. And let's get rid of some of this other stuff and move this up so we can keep working on this. So now we just have a pretty simple integral here. And of course, notice that we're going from 0 to 60, where 0 to 60 is going to be h. So we're starting with h equals 0, which is when the bucket's at the bottom, and when h equals 60, that means this h has gone all the way up to the top here, and our bucket's at the top. So that's where we're getting our limits from. So now we can go ahead and sub in for our density of the chain, which was 0.5 as we did before. And now we can go ahead and solve this integral pretty simply. So we basically just use the inverse power rule, and we get this integral here evaluated at 60 and 0. So if we go ahead and plug 60 and 0 in for h here, we get this. And if you go ahead and crunch those numbers, we end up with 900. So 900 is our new work required to move that chain up. And you notice it was a bit less than what we had before. Before we had 1200, but 1200 was an overestimate. So 900 seems like a good number, right? It's in the same ballpark, and it's less than what we had overestimated before. And this is actually going to be the exact work required to move that chain up by this method. So our total work now is going to be 3,000 foot-pounds. And we can go ahead and block that in the red, except this time we don't have to caveat this with anything. This is the exact amount of work required to move this bucket up via this chain. So this is how you do a pulling problem. It's not necessary to do all those the steps I did before where we separated into 3 increments. I was just trying to illustrate this idea of how we get to this integral. Working one of these problems, you probably just want to jump straight to the integral, because that's what's going to give you this exact value that we ended up with here.